Hi everyone, I will be talking about anonymous quantum money, upgradable quantum coins, and quantum voting. Okay, let me first start by recalling what quantum money is. In quantum money, we consider that there is a quantum bank who produces quantum states called banknotes. And our first requirement is correctness, which says that honestly generated banknotes pass the verification with high probability. And our main security requirement is the so-called counterfeiting security, which says that which is modeled as the following security experiment. We consider some efficient adversary who receives some number of banknotes, and it tries to produce at least one more banknote. And then these alleged banknotes produced by the adversary are verified, and we require that the probability of all of these k+1 banknotes passing verification at the same time is at most negligibly small in some security parameter. And this means that the adversary cannot produce even a single additional banknote. And there are mainly two types of quantum money schemes, the so-called private key and the public key schemes. In the private key setting, when a user is given an alleged banknote, it needs to talk to the bank to verify the authenticity of the banknote. And in the public key setting, there's a public verification key using which any user can verify the authenticity of an alleged banknote. And one issue with the private key setting is that it's kind of impractical. You need to talk to the bank all the time, and there's like a single point of failure. If for some reason the bank is down or you cannot communicate with them, you cannot do any transactions. And in fact, for the private key setting, you can kind of simulate the situation using something called eCash. You don't really need even quantum information. You can kind of do something similar using classical crypto. For that reason, in this talk, I will be focusing mainly on the public key setting. So there have been various constructions for both the private key setting and the public key setting in the literature so far, starting with the very first construction of Wiesner, and there are like more recent and modern constructions like the so-called pseudo-random states and subspace states and so on. So in almost all of the constructions in the literature, the banknotes kind of follow the following template. There is a classical serial number, and the quantum state part of the banknote is a quantum state that is associated with this classical serial number. And in fact, again, in almost all constructions, there's also a classical digital signature signed by the bank on the serial number of the banknote. There's kind of one main exception to this template, which is the quantum money constructions based on pseudo-random states, which are just efficiently preparable states that are indistinguishable from hard random states against all efficient adversaries. But one issue with the pseudo-random state-based quantum money constructions is that there is some evidence showing that it's really hard to make them publicly verifiable. So you're kind of stuck with the private key setting in that case. So for the purposes of this talk, I will be ignoring the pseudo-random states. So as I said, in almost all the constructions, banknotes consist of some quantum state and some serial number, and even a signature on the serial number. And this kind of makes the banknotes trivially trackable. For example, some adversary can just record the serial numbers of all banknotes it sees, and later on, if it sees the same banknote again, it can infer some information about the people who are using the banknote and what they're buying and so on. And in fact, this method is already used by the law enforcement for tracking classical paper banknotes that we're using today. And even amateur websites like this website, for example, have been able to track like hundreds of millions of banknotes all over the world just by recording the serial numbers. And the privacy of our spending is kind of essential because like if someone can track your banknotes and your spending, they can possibly infer things about your travel history, your purchasing habits, your family members maybe, and so on. In fact, the privacy has been the focus of various classical cryptocurrency projects like Zcash and Monero. So to recap, we can say that privacy is really important for cryptographic money schemes, but the current constructions of quantum money trivially have no privacy at all. They're trivially trackable. So to resolve this, we show various constructions that satisfy various degrees of privacy. First, we show how to construct a so-called public key quantum coin scheme where all the banknotes look exactly the same. And as a related application of this scheme, we actually also show how to construct a so-called upgradable public key quantum money scheme, which I will explain later. Again, as I will explain later, the quantum coin schemes, they do satisfy some notion of privacy, but they do not fully capture fully malicious privacy security against fully malicious adversaries. So we also formalize what is meant by privacy for quantum money schemes through definitions like anonymity, traceability, and untraceability. And we show how to construct a public key quantum money scheme with anonymity and traceability. And again, I will define this later. We also show how to construct a so-called untraceable public key quantum money scheme. And finally, this might be a somewhat unexpected application, but we also show, using our techniques for the quantum money schemes, how to construct a quantum voting scheme with universal verifiability, which means that when you're voting, you just post your vote on a public bulletin board, and anyone in the world can verify your votes. And it satisfies full privacy against even the voting authority itself, who generates the voting tokens. And the votes are classical, so you just send a classical message to some bulletin board. All of these in the common random string model, which only assumes that there's a honestly sampled uniformly random string and no other assumptions, except some cryptographic assumptions like obfuscation. Okay, so first let me start by defining what quantum coin is. In a quantum coin scheme, we require that all the banknotes produced by the bank are identical pure states. And this gives us some anonymity in the semi-honest setting where you're trying to track banknotes by simply recording the serial numbers. Here they will be identical, so there's nothing to distinguish by just recording information. So in the semi-honest setting, you're not allowed to modify the banknotes. And I want to note that even in the semi-honest setting, the previous works only obtained quantum coins in the private key setting, which, as I said, is kind of impractical. So our work is the first to obtain public key quantum coins. And finally, we also show how to construct public key quantum coins, only assuming collision-resistant hash functions and something called subspace-hiding obfuscation. So as I said before, as a application of our quantum coin techniques, we also introduce a notion called upgradeable quantum coins. So let me tell you what the motivation is for upgradeable quantum coins. So one of the biggest problems in theoretical quantum crypto is constructing public key quantum money from mild cryptographic assumptions. But unfortunately, so far, only provably secured constructions from standard assumptions require obfuscation, which is a very heavy cryptographic assumption. And in fact, in the post-quantum security setting, we don't even have any secured constructions of obfuscation. So as a possibly temporary solution, we introduced the notion of upgradable coins, which kind of proceeds in two phases. So since the quantum banknotes will be identical states, in the phase one, we will only assume some mild cryptographic assumption, and we will have a kind of restricted notion of public verifiability, where to verify an alleged banknote, you just do a swap test with your existing banknotes. So this is kind of restricted in the sense that you cannot receive huge sums of money because you need to be able to compare them to your existing honest banknotes that you know to be honest. But in that case, you can just go to the bank to verify their authenticity. And for small amounts, you can do this swap test. And in phase two, once we are able to construct, for example, obfuscation schemes that are post-quantum secure, the bank just publishes a classical string publicly, and suddenly we are able to switch to full public quantum key money, public key quantum money. And we show how to construct a public key upgradable quantum coin scheme where in the phase one, where you can only receive small amounts of money in the local verification setting, you only assume security of public key encryption and collision-resistant hash functions, which are commonly accepted standard cryptographic assumptions. And in phase two, once we come up with a, for example, subspace-hiding obfuscation scheme that is quantumly secure, the bank just publishes this classical string using this obfuscation scheme, and suddenly you're able to use this quantum money scheme in the full public key setting. Okay, so going back to privacy, as I said, quantum coins only provide some kind of semi-honest privacy, and to remedy this issue, we've introduced formal definitions for privacy in the cryptographic sense. So our first definition is called fresh banknote indistinguishability for anonymity. We modeled this as the following security experiment. There's a bank setup who produces a minting key, a banknote verification key, and the tracking key that I will explain later. But this tracking key is only given to the law enforcement, and the users or the mint don't have this key. So the adversary receives this minting key and the verification key, and it produces some quantum state, an alleged banknote, which is then verified by the challenger. And then we flip a coin, and the adversary either receives the same state back, or it receives a freshly generated banknote. And we require that the adversary cannot tell which case it is. So this says that even the mint who produces these banknotes cannot distinguish a banknote it has seen before, or even it has produced itself before, from a fresh banknote, which means that it will not be able to track any banknotes. And this implies anonymity definitions given in various previous works. As an orthogonal definition, we also introduced the notion of traceability. So here there was the minting key, which allows you to produce banknotes, but there's also a separate tracing key, which is only given to the law enforcement. And we require that no adversary who receives some banknotes can produce a banknote that has a different hidden tag that was not included in any of the original banknotes. So this means that the owner of the tracing key, the law enforcement, can perfectly track banknotes, whereas people who don't have the tracing key, which includes all the users and the mint who produces the banknotes, they have no ability to track any banknotes at all. Of course, you might think that, for example, maybe I don't want the law enforcement to track the banknotes either. Can we have some notion where no one at all can track banknotes? So in this case, we still need some kind of setup assumption, because if there's no trusted setup at all, it's possible to show that this is impossible. But our assumption is very mild. We only assume that there's a honestly generated uniformly random string, and the adversary receives this random string, and it produces all the keys, the verification key or the banknotes, the minting key, the tracing key, possibly everything, and it also produces a alleged banknote. Then the challenger verifies this alleged banknote with the maliciously chosen verification key. And then we flip a coin, and either we give back the same state to the adversary, or we produce a fresh banknote using the malicious minting key produced by the adversary. And still, the adversary cannot distinguish which case it is. So this means that just assuming this uniform random string, even if the bank and the law enforcement and everyone are, even if they are all malicious, still they will not be able to track any banknotes. Okay, so let me also talk a bit about the connections of this untraceability notion to the voting application. So as we will show later, the untraceable quantum money construction we give, in this construction, the banknote states are actually kind of functional in the following sense. If you measure the banknote state in the computational basis, you receive a measurement result that can be verified to be an actual computational basis measurement result from some banknote. And again, if you measure the banknote in the Hadamard basis, again, you get a measurement result that can be verified by anyone with the public verification key to be an actual Hadamard basis measurement result. And thus, we can actually see these measurement results as a vote for candidate 0 or candidate 1. And by doing this in parallel, you can vote for, you can have a voting scheme for any number of candidates. And the security notion we require is that someone who has K voting tokens should not be able to cast more than K valid votes. And this is kind of related to the unclonability notion that we have for quantum money. We show that no adversary can output correct measurements for both bases given a single copy of the state, or if they are given K copies of the state, they cannot output K plus 1 different valid measurement results. And by this property, we get the voting security, which says that everyone can only vote once. And in our scheme, the votes will be classical because they are just measurement results. So the users just post their measurement results or votes online. And again, by the public verifiability property of the quantum money scheme, the votes also can be verified by anyone in the world, essentially. Of course, this doesn't follow directly formally by the verification property of the quantum money scheme, because in the quantum money, you're verifying a state, whereas here, you're verifying a measurement result, which is kind of harder to verify. But we're able to show that we can actually do this. And again, by a connection to the untraceability property, we are able to show that the privacy of the votes holds even against a corrupt voting authority who creates the voting tokens and even the vote verification key and everything maliciously. We only assume a honestly generated uniform random string that's available to everyone. And our voting scheme also satisfies anonymous delegation. And I also want to note that the notions we have here for our voting scheme, like this full privacy and the security of voting, which says that you cannot vote twice, this is actually impossible to obtain at the same time using a classical scheme. Because in a classical world, we can kind of remind an adversary to vote twice, and even if even the voting authority cannot tell the difference, then they will not be able to reject the duplicate vote. So this is a uniquely quantum notion for voting. Yeah, I think we don't have too much time for construction details, but we can follow with questions.
Thank you very much. And there are any questions from the audience? Please.
Thank you very much for the nice talk. So I think I remember that you in the beginning said what assumptions you need for construction of untraceable quantum money, but then after the definition I had forgotten already. Can you repeat what assumptions you need for construction of untraceable quantum money?
Yes, you mean like the setup assumptions or the crypto assumptions or both?
Both.
Okay, both. Yeah, as a setup assumption, we only require a common random string. And as the crypto assumptions, we require obfuscation and LWE.
Okay,
Yeah,
thanks. I just asked because I guess the untraceability definition is very strong.
Yeah.
I like that.
But I think, I guess common random string is as weak as it gets in terms of
Right.
the setup assumption. Yeah.
Thanks.
So thanks for your very nice talk. And I have like 2 questions. So one question is you are doing this in a common random strings model. So but in practice, how can you put it in practice? Because if the string is not common, maybe it's published by the authority. Then if it's not random, if they choose deliberately, is the privacy be like affected? And the second problem is that you say this voting system cannot be achieved classically, then maintain privacy and some properties. But can you do it with digital signatures like this classical cryptography are doing? So thanks.
Yeah, thanks for the questions. So for the first question, as you said, it's kind of not nice to assume this thing about an honestly sampled common random string, because when someone gives you a string, you cannot really verify that it's been sampled honestly and randomly. But this is a problem that people have thought about a lot in the crypto community for years. There are various methods. For example, you can have like a multi-party computation between multiple trusted parties, and if you only trust even like some of them, you will be able to trust the output string to be like kind of uniformly random. And it would be great to not have this assumption, but I think it's impossible to have this strong notion of untraceability without any assumptions at all. And I think this is as weak as it gets in terms of the set of assumptions. And for the second question, you said that even with like crypto techniques, are you asking if we can get this classically, this voting scheme? Was that the question?
So because my problem is like, so maybe your scheme is like informational secure, and the classical one with digital signature is just computationally secure.
No, our scheme is also only computationally secure.
Okay. But I think with classical, with the digital signatures, can also achieve like privacy and not forgeability, right?
So you can get some kind of privacy. That part is fine, but the harder part is achieving privacy and at the same time preventing duplicate votes.
Yes, but I think in classical, like they could like of course, that maybe they require some authority offline. Them you go to present your ID, and then they give you a digital signatures on that. And yeah, but maybe they require more like assumptions on the authority. But maybe your scheme is like require less assumption on that. But but because you, I mean, there's not an actual protocol here, so I just wondering about that.
I see. I think, yeah, so you can kind of also formally prove that you cannot achieve this classically. Maybe you can discuss offline.
Yeah, okay. Yes. So,
Thanks.
thank you. Thanks for your talk and thanks for your answer.
Thanks.
Okay, great. So let's thank Dr. Cakan for the talk.